Hello, this is the second lesson, lesson 2B, in the part of machine learning and cloud services, which discusses optimization in general. And we'll discuss in this lesson distances and funny spaces and heuristics. Initially, we'll do distances and funny spaces, key to machine learning. So if we look at most machine learning, we have to first find the distance, because we need to compare points. And we need to say which points are near each other. So to do that, we set up spaces and points in those spaces. So if you do so-called recommender systems, there is a so-called user-based collaborative filter, where we think of the users as points in a space, where the dimension of the space is the items, so that every user is associated with a point in that space, depending on what items they purchased or like. So then we have users represented as a vector in item space, and the ratings of the fact that the user has seen a particular thing, where the ratings are 0 or 1, are just components in that item spaces. And we're trying to find, so we have vectors, which are sort of a bit peculiar, because some of the items you've not seen at all, and there's a difference between a rating of 0 and not seen. So actually this space is not a true vector space. It's a vector, but not a vector space. And we still want to find users which are near each other. And we only need to count the items where they've both actually seen the item in calculating the distance. So that's why I said the number in common is pretty small. And the Pearson coefficient is ingeniously designed to be a distance measure that only sums over the items that are seen by both users. So this technique is used in practice for songs by Last.fm, Netflix, and so on. And now we do item-based collaborative filtering, which is another way of doing recommender systems. We think of items in a space, where the different dimensions in the space are the users. So this one is sort of the opposite case, where if you have m users, this is the dimension m, which can obviously be very big, and there are probably more users than items, typically. And we have the same thing, it's a vector, and many items only have some number of users in common. And in calculating the distance between items now, as opposed to the distance between users, we need to just involve the items that have been associated with both users. This is where we see the cosine measure, which only sums over users that rate both I and I prime. So again, this is a distance. It is not a vector, because the vector has three values: a rating or a yes/no, so it has item which has a value, or it has never seen it, which is not a 0. So you can't use 0 as the case as they haven't seen. All right, now we have content-based recommender systems, where we don't use the users, but we still have items as the points, and we're classifying the points based on their properties. Are they pink or big, or are they animals? Are they old or new, and things like that. And so we have probably not as many, so this is not as high a dimensional space. We have a vector in property space, and we want to look at items that are near each other in this space. Properties could possibly be defined for every item. So this might be even slightly nearer a true vector, but it's not nearly as big a space. So here in this simple case of recommender systems, we have three totally different spaces: two for items where the dimensions are either users or properties, and one for users where the dimensions are items. So we have AI analysis, we always get points. Events, when we're doing physics analysis from these accelerators, they generate events, which are points in some space. Users or items are points, and they're all within a space or a bag. Sometimes you talk about bags, and that just points out the space is not a real space. It's just a collection of points. And they say we only know the distance between the points, they're not vector structured. But anyway, we almost always can find a distance. And this distance has the following features. It's always larger than naught, bigger than 0. If their points are very near each other, the distance is very small. And typically, you always define the distance so it's symmetric. Namely, distance from A to B is the distance from B to A. And there is a triangle inequality, a very famous inequality, that D, which is true in Euclidean spaces, that the distance from A to B plus the distance from B to C is greater or equal to the distance from A to C. That is typically not true in these funny spaces, because the funny spaces have no reason for this to be true. This triangle inequality needs real vectors to be true. So to use distances, well, we have nearest neighbor algorithms. Those obviously just unique distance. If you want to find points near, you have a point, you want to find points near it, you just need distances. I mean, you can trivially do that by sorting on the distances from, you have a given point, you just calculate the distances, you just calculate the lowest 3 or the lowest 4 distances. Very straightforward, limited sorting problem. And then I've already shown you that clustering can divide space into regions based on these distances. And then there are other methods like Gaussian mixture models, latent semantic analysis, or latent Dirichlet allocation, which are a more sophisticated way of dividing space into regions based on topics or latent factors, as well as explicit values from the point nature. All right. The last part of this lesson is on heuristics. There's a good Wikipedia article. Wikipedia usually is okay, and it's, I think, okay on heuristics. And what are heuristics? It's a method which is problem specific, where it's often much faster. And people always talk about MP hardness, the problems of exponential in complexity. But actually, if you look at what's hard in the real world, when you're allowed to use heuristics, it doesn't necessarily correlate with MP hardness. It could be that polynomial algorithms, which are actually impossible to solve in practice, just the only thing which is typically always soluble are linear algorithms, because that means they scale like the number of points. Well, to get the points into the computer, you probably have to do something that scales like the number of points. So an algorithm that's linear in the number of points is going to be always straightforward. Algorithms which are square in the number of points, when you start getting millions to billions of points, is very, very hard. And clustering is actually not only, it's MP hard, but its heuristics can actually be order n or order n squared. And again, the clustering heuristics are very powerful. And say the study of what's hard as opposed to what's exponential are different studies. They sometimes are totally correlated, that hardness and exponential time complexity are totally correlated, but often that's not true. You can solve the exponential complexity with an algorithm, heuristic, and then we have to ask whether there's heuristics order n or order n squared. And I pointed out that in clustering problems where you only have distances, they're always order n squared and quite hard in practice to solve with big problems. We do any of these collaborative filtering algorithms, they go like the number of customers times the number of points. Clustering depends on heuristic, but k-means goes like is linear in the number of points in vector spaces. The combinatorial optimization approach is exponential. And another important point in studying all of this is to note that data is not precise. And we don't actually need to get the exact answer, because the data is approximate, it's inaccurate, it's scruffy, it's wrong from time to time. So we don't have an exact data, and we often don't have an exact problem. And so this is another reason why heuristics are very powerful, because they tend to give approximate answers, but maybe all you want is an approximate answer because you have approximate data. And so this insisting on exact answers and combinatorial optimization may not be the best thing to do in practice. Thank you.